What if fields as vast as algebra, topology, even logic itself could be described in a single language? Not just described in it, but built from it, with its rules, its structures, and its proofs all living in the same universe. That's the promise of homotopy type theory, a new foundation for mathematics, where equality is not just a yes or no statement, but a path with shape and structure. But hang on, what do all these symbols mean? What even is a type? Well, we can think of a type as a space. This space is inhabited by things called terms. These terms could be numbers, functions, or even types themselves. At this point, it would seem that types are the same things as sets. However, types and sets are fundamentally different from each other, and the distinction lies in the way types handle equality. Perhaps an example might explain things. Suppose we had a type A, and suppose it is inhabited by the terms x and y. Note that we use a colon to denote that terms inhabit a certain type. In homotopy type theory, two terms are seen as equal when there's a path from one to the other. In our case, that would be a path from x to y. However, this is where things get interesting. In homotopy type theory, we can have multiple paths demonstrating that x is equal to y. Let's draw another one. Let's call these paths P and Q. We denote this by writing that P and Q are inhabitants of the equality type x equals y. An equality type is a special kind of type that contains proofs that one term is equal to another. And we can go one step further. We can ask if the path P is equal to the path Q. In that case, we're not simply speaking of a path, but of a path of paths, something that looks a bit like this. Topologists refer to these paths of paths as homotopies, hence the name homotopy type theory. And yes, if you were wondering, we can go a level higher. We can speak of paths of paths of paths, and paths of paths of paths of paths. We can go up to infinity. But that's a video for another day. Thanks for watching.